Hi everyone, welcome to our class. So unfortunately, due to the current COVID situation, we have to give this at least this lecture online. So here at our Tencent meeting. So I think maybe let me at the beginning of this class to introduce basically to give you a few announcements. So the first announcement is assignment 5 will actually due in 1 week, which is basically this time, but a week later. That is basically November 29th at 3 p.m. So please keep in mind and make sure that you submit assignment 5 on time. So the remaining arrangement for the rest of the semester. So basically, we have 15 classes this semester, and I will teach for 13 times. So this is the 12th time. So today we are going to finish the part of complexity theory. And for the last week, I will very briefly talk about approximation algorithm. So since basically for today, we will introduce NP-Completeness and also some further complexity classes. So in general, we know a lot of problems are actually very difficult to be solved. But actually, maybe if maybe you don't want to find perfect solutions, but relatively good solutions. That is to say, if we want to give approximation algorithms. And typically, I mean, for many problems, we can actually make some progress along that. So we actually make a brief discussion. I mean, after we have introduced the complexity theory, we will introduce some approximation algorithms. And I think this is basically the last time for my teaching. And I will also make a brief course summary and also a brief discussion about like the final exam. So how will the final exam will work? So for the week 14th, we will basically have presentations. So currently, as I see, I think there are currently 15 students selecting this course. And I think for each lecture, we basically have like 3 hours or so. So basically for the presentation, for each student is going to make a brief presentation for 10 minutes. And I think for basically the TA will actually make an online document, online Excel to make to basically ask for your time availability, and maybe you can just fill in the gaps there for the schedule that you want to choose. But that is basically for the class for week 14 for the presentation schedules. And basically for the last week, for week 15, we will have a final exam in class. Although I'm not totally sure, I mean, this is probably also going to depend on the COVID situation. I mean, whether we are going to have like in classroom exam or it is okay to have an online exam. I think this is probably still need to yet to know due to the current, I mean, in general, the current COVID situation and the policy then. But I will definitely keep you posted. And I think, unfortunately, today the lecture has to be given online. I'm not totally sure what is going to happen for the next week. I mean, the last week for my teaching. I think with high probability, it will probably also take place also online, because I think in general, I mean, the COVID situation in Beijing is not so optimistic. So I think with a decent probability, the incoming lecture will also take place online. But I'll actually keep you posted both on I think mainly on the on emails, and also I will post an announcement. I mean, for the course format for the next week in our in the course.pku.edu.cn. So that is basically a brief discussion about announcements. So is there any question about like, I mean, the arrangement towards the end of the semester? Okay, so if there is no question about the announcement, so let's actually talk about the thing that we need to talk about today. So basically today we will need to continue to talk about complexity theory. So I think basically for the last time we talked quite a few, I mean, different reductions. I mean, basically, I mean, inside a complexity class of NP, we can consider reductions of different problems. So here in this class, I mean, in general, we will prove some actually quite solid results. So we will have actually at the very end of the next lecture, we have the definition of NP-completeness. So basically, we say that a problem Y is NP-complete if Y is actually an NP problem, and actually, on the other hand, for any X, for any other NP problem X, there is this polynomial time reduction from X to Y. So such kind of problem Y is called an NP-complete problem. And basically, I think, I mean, this is still like a little bit abstract definition. And I think I probably need to work a little bit more details and actually to prove some of the NP-completeness of some of the problems. Okay, I see a question here. So let me see, what is the question? So what will be the project report deadline? The project report deadline will be the end of the week 14, which is announced in our course website. That is to say, I mean, the end of week 14, I think that is going to be, let me see, that is going to be December 10th. Oh, excuse me. That is going to be December 10th. I will make another reminder. I mean, I think for the next class. So basically, for tonight, I think we will probably need to settle down the schedule. Basically, for the week 14, I mean, which slot you would like to pick. So I will actually make an announcement for that, and I will make another reminder. I mean, I think there are still like basically around 20 days or so towards the deadline for the final report. I will definitely remind this. I think to make sure that you can meet the deadline. Okay, so any other questions? So maybe, I mean, before we talk furthermore about NP-completeness. Okay, so let's continue with the course today. So basically, as I just mentioned, last time we have this definition of NP-completeness, but I guess this is still, I mean, this is still a little bit too abstract. I guess maybe we want to like further like fulfill this and basically have like a better understanding about what NP-completeness is. So let's actually continue our journey here. So first, maybe we want to, I mean, have a better understanding about like how powerful like NP-completeness problems are. So the first thing that we want to show is that basically we have such kind of like a theorem here. Okay, so we say that suppose Y is an NP-complete problem. So we say that then Y can be solved in polynomial time. I mean, this sounds really, I mean, really strong. I mean, we are talking about an NP-complete problem, and we say that actually the case where Y can be solved in polynomial time. So we want to prove that this is the case if and only if actually P equals to NP. So clearly you can see this is really like a strong condition here because I mean, for most of the NP-completeness problem that we have been talking about, I mean, for all of them, I mean, currently people have not figured out like a polynomial time algorithm for any of them. But actually, on the other hand, this is like a really a strong restriction here. So if you can figure out like a polynomial time algorithm for NP-complete problem, then basically you just show NP equals to NP here. So actually, like an NP-complete problem can be solved in polynomial time if and only if P equals to NP. So this is really strong, and I guess we probably need to prove this. So this is not so hard to prove. So because we are talking about like a if and only if condition, so let's also actually talk about both directions. So actually, from the left-hand side to the right-hand side, so let's say suppose Y can be solved in polynomial time. Okay, so in this case, I mean, we are talking about like an NP-complete problem. So let's say that we have like an arbitrary, I mean, a problem in NP. So let X be any problem in NP. Okay, so we know that Y is actually an NP-complete problem. So we definitely know that X actually there is a polynomial time reduction from X to Y here. So we know that this is true. And actually, since Y can be solved in polynomial time, we know that actually we can solve X in polynomial time. Okay, so we are actually taking an arbitrary problem X, I mean, from the set NP here. And actually we have given like a polynomial time algorithm of X based on reduction to Y here. So basically this implies that actually NP is a subset of P. But actually, on the other hand, we actually definitely know that P is actually a subset of NP here. So we know that P is actually a subset of NP. So this just implies that actually P equals to. So this is the first direction. So how about the other direction? The other direction is actually also quite trivial. So if actually P equals to NP, then basically we know that actually we are taking, I mean, we are talking about the NP-complete problem. Y is actually taking from the NP side. So actually Y is taken from NP, but under this assumption that P equals to NP, we know that actually Y belongs to P. So we know that Y can be solved in polynomial time. And this finishes the proof of the theorem. Okay, is there any question here? Okay, I think this should be relatively easy to digest, right? So let's actually take a look at a further theorem here. So still about like the relationship for related to NP-complete problems. So suppose actually, Y is an NP-complete problem. And actually we have another problem Z, which is also actually an NP problem. And we know that actually Y can be reduced to Z. Then basically we are pretty sure that actually Z is an NP-complete. So the intuition here is that actually we have already assumed that Y is actually a difficult problem. It's already an NP-complete problem. But you can actually further, have like a problem Z, which is still in NP. And actually, on the other hand, you have a polynomial time reduction from this difficult problem Y to the problem Z here. Then this really sounds strong. And the fact is that we can prove that Z is actually an NP-complete problem. So the proof is actually quite straightforward. So actually, for any X in NP. So we just take an arbitrary NP problem X here. So we know that actually Y is an NP complete problem. So we know that actually X can be polynomial time reduced to Y here. And given our assumption, we know that actually Y can be polynomial timely reduced to Z here. So this just implies that actually X can be polynomial time reduced to Z here. So actually we are taking, on the other hand, we are taking an arbitrary NP problem X here. So basically this is just going to imply that Z is actually NP complete. Okay, so any questions? Okay, so if there is no question, I guess, basically for the last class and for this like two very easy to prove theorem, I guess this is still, about like reductions between problems. I guess in general, a very important and a fundamental question is that we definitely want to give some natural problem that are actually NP-complete problems. So a fundamental question here is that actually do there exist natural NP-complete problems? Okay, so this is something that we will actually give like a heavy introduction today for like an hour or so. So we basically discuss about how we can actually prove that some natural problem is actually NP complete. So to do that, actually, we are going to look at a specific problem that we will think about. So this problem is called a circuit set problem. So for the circuit set problem, it actually arrays like this. So basically, we say that actually we are given a combinatorial circuit. So basically, for a combinatorial circuit, is actually built out of, just like common logical gates like AND, OR, and NOT. So it's built of this very common logical gates. So where we also have some discussion about like the inputs. So basically, we assume where the circuit, let's say, may have hard encoded inputs. So I will introduce what this means in a minute. So the question is that is there a way to set the circuit? So basically to set the circuit inputs so that output is 1. Okay, so let's, for instance, take a look at an example here. So let's say, for instance, like example is probably going to look like this. So maybe we will actually throughout this part, we will basically use this for the AND and basically for this, for or, and basically use this for not. I think these are actually a quite standard notation in terms of Boolean algebra. So basically, we will use these notations to represent and, or, and not gates respectively. So for instance, we can maybe think about like a circuit like this. So let's say that maybe at the beginning, maybe we have an and maybe here we will have like a not here, say, and maybe we have like an and. We can have like a and here. And maybe let's say we have an or here, and let's say we have an or here. So here we actually have a bunch of different inputs. So basically we have assumed that maybe the inputs is actually like this. So here we mentioned that actually we will have some hard encoded inputs. So this is actually possible in our current circuit. So maybe for this case, we can assume that maybe we require that, for instance, the first input is 1, like the second input is 0, and you have the freedom maybe to choose like the later 3 here. So maybe you want to think about like choosing like what kind of values you can make this circuit to actually have this output. I mean, for the output here to give a value of 1 here. So let's say this part is actually the hard encoded. And actually, these question marks are the inputs that you are supposed to make. So actually, for this circuit, there is actually a solution for the set problem that basically have arrangement for all the question marks, and you can give an output that equals to 1 here. So let's see, for instance, and yes, instance is like 101. So for instance, assume that maybe you have like a 1 here, maybe you have a 0 here, maybe you have a 1 here. So we just do this layer by layer and see what is the corresponding values. So here, basically for the end here, basically you got a 1 here. And basically you have this OR function here. You actually got a 1 and you got a 1 here. And actually here, I guess you have the OR here. So for the OR here, you actually also you get, sorry, I think I made a mistake here. So I have the end here of 1 and 0 here. So this should be 0 instead of 1. But for the OR here, you actually got a 1, and actually for the other OR, you actually got a 1 here. Oh, I think I probably made another mistake in drawing this circuit. So let me see. Well, I guess I probably shouldn't have this line. I think having this line is actually quite weird because the not, I mean, for the not function, I guess basically, I mean, for not, I mean, it's basically for the not, it is going to map 1 to 0 and 0 to 1. I'm not sure why I'm here drawing another line because it's supposed going to only have 1 input here. So basically like this. But nevertheless, let's take a look at this corresponding circuit here. So basically, we know that basically we know that the value here should be a 0, and actually the value here, basically the value here should be a 1 here because the OR of 0 and 1s is just 1, and here also, I mean, the OR of 0 and 1s is just going to be 1 here. So here, let's look at the next layer. So we have a not for 0 here, so this is going to be a 1. And here we are going to have a 1 and of 2 values, which are both 1 here. So this is actually going to be a 1 here. And basically the end of 1 and 1 is just 1. So this is just going to mean that we are actually having a valid solution. Okay, so any question about the definition of the circuit set problem? Okay, so if there's no question, I guess a very important main result that we are actually going to prove today. A main theorem that we are going to prove. So this is actually originally proved by Cook and Levin. So we just call this as a Cook-Levin theorem. So Cook and Levin basically proved that actually the circuit set problem is actually NP-complete. And in addition, the circuit set problem can be polynomial time reduced to the 3-set problem. So basically, we know that the three-set problem is actually NP-complete. Okay, so this is the main result that we will prove today. So before actually we make the proof here, let's also make some discussion. I guess basically at the beginning of today, we have these theorems. So let's see, actually assume the correctness of the Cook-Levin theorem. There are some immediate consequences here. So basically we know that, note that, so we have actually proved that actually for the three-set problem, there is a polynomial time reduction to the independent set problem. And actually to the vertex cover problem. And also then to the set cover problem. And at another clue, we have proved that the three-set problem can be polynomial time reduced to the three-color problem. So this will actually imply that actually all these problems that basically independent set. Vertex cover, set cover, three color. They are actually all NP complete. So this is actually very powerful because, I mean, the three-set problem, this is a natural problem. So we basically, the Cook-Levin theorem proved the NP-completeness for a closely related problem called the circuit set problem. I guess actually beyond that, based on the circuit set problem, they also further prove polynomial time reduction from the circuit set problem to the three-set problem. And basically after, on the other hand, we have establish another chain of polynomial time reductions to the independent set problem, vertex cover, set cover problems. And on the other hand, the three-set problem can also be reduced, polynomial time reduced to three color problems. So this is just going to say that all these problems are going to be, all these natural problems are actually NP-complete problems. So any question on this? Actually, I think I'll meet it at 1 here, sorry. Okay, so if there's no question, I guess let's continue to give a complete proof of the Cook-Levin theorem. I mean, to prove the Cook-Levin theorem, I think we actually have two steps. So the first step is that we will actually first prove that actually the circuit set problem is NP-complete. I mean, to do that, basically, I mean, we just show that actually for an arbitrary NP problem X, it can be polynomial time reduced to the circuit set problem. So basically, this is the first thing that we are going to prove here. So, I mean, in general, let's think about, I mean, I guess this is basically a place where actually for an arbitrary NP problem, we actually make a reduction to the circuit set problem. So actually this really utilizes the structure of the circuit set problem. I guess in general, you can clearly see that this circuit set problem is actually just composed of AND, OR, and NOT gates. And it is in general known that basically the AND, OR, NOT gates, they're actually universal. That arbitrarily, I mean, basically arbitrary this kind of a Boolean computation, they can just be decomposed into AND, OR, and NOT gates. So this is probably just suggesting that this circuit set problem, I mean, based on circuits and based on the assumption that actually you may also actually, on the other hand, have like hard encoded inputs. And also you can have some question mark, so you can later designate them to be 0 or 1 here. So this somehow suggests that this circuit set problem is really like, I mean, in general, for like an arbitrary computational problem, you should be able to turn this into like an arithmetic circuit. I mean, based on this kind of and or not, and basically also the input should be able to be represented by 0 and 1s here. So this is just like a high-level intuition, I guess. I mean, in general, this is true. So we probably not going to cover all of the details here, but we mentioned such kind of effect here. So effect. That actually any algorithm that actually takes a fixed number of inputs. So we say that let's say that the length of the input is n bits, and like produces yes or no answer can be represented by a combinatorial circuit. Basically, as we just mentioned, we just use the AND, OR, and NOT gates. And actually, they are just universal, and an arbitrary Boolean computation can be represented by AND, OR, and NOT. And moreover, because we are talking about an algorithm that basically in NP, so basically we say that actually in general, I mean, we have such kind of like an algorithm, and actually if the algorithm, I mean, let's say if it takes actually poly n steps. So if an algorithm takes poly n steps, basically we know that the circuit actually has a poly n size. So this is a common fact that we will probably not prove here. So this is just like a very standard that in general, if we want to consider like a computational problem, we can just regard, I mean, we have like a circuit to calculate this, and this circuit is built out of AND or NOT gates. So we basically build on this fact to prove what we need today. So the first thing, as we just mentioned, is that we will need to prove that the circuit set problem is actually an NP-complete problem. So let's actually do that. So proof. So I mean, we just take an arbitrary problem. We just take an arbitrary problem x from the NP side. So basically, since we know that actually x is in NP, x actually has a polynomial time verified. So basically, something like this. So basically, this is the input, and this is the verifier if your input is actually going to be in this problem. Okay, so this is still like a very general and abstract discussion. So let's actually continue to make a further discussion on this. So actually to determine, actually for instance, like whether a string s is in this problem x, maybe for some specific string s. So let's say that s actually has length n here. So basically we need to answer. Actually, is there a t of length Pn, where here, I mean, this P just come from this verifier, and actually we know that P is actually a polynomial. Such that B as T actually returns yes. So this is just like a formal way that we want to write down basically the definition of NP here. But actually, on the other hand, we know that here the B here is a polytime verifier here. But actually, this verifier, I mean, for different parts S and T here. So do you feel that somehow it is actually quite similar to this circuit set problem here? So basically, we have a part of hard encoded inputs, and basically under the assumption that we have this part of hard encoded inputs, we can have our choice of the inputs, the question marks here, and want to determine whether this problem has like a positive answer or not here. So basically, we then say that we can actually reduce basically this problem x to circuit set as follows. So how we are going to do this? So basically, we are just going to view a B here. So the B here as an algorithm on n plus Pn, but this is still a polynomial. So basically, we assume we just regard this B here as an algorithm on n plus Pn bits, and actually we just convert it. So we convert it to a polynomial size circuit. Basically with n plus Pn inputs. So how do we actually specify this? So basically we say that the first n inputs are actually hard encoded with the value of s. And I guess on the other hand, it is imaginable that for the remaining Pn inputs, so actually we just label them just by just variables. So like the question marks above. So we just label them by variables representing the bits of t. Okay, so a quick observation here is actually by the definition of NP. So basically, we know that S belongs to X, if and only if there is a way to set the input bits to K, so that the circuit outputs a 1. Basically, just equivalent to returning a yes here. And this is just to say if and only if K is satisfiable. So this just actually just establishes the fact that actually X can be a polynomial time reduced to a circuit set problem. Okay, so you see that, I mean, I kind of feel that this proof is a little bit superficial, but in general, I mean, the intuition is that just like this fact here, that actually any algorithm that takes a fixed number of n bits and basically the corresponding circuit sets have like poly n steps. So basically, we know that this is the case for an algorithm. And in general, for an NP problem, it actually for a problem in NP, it just naturally have two parts. So basically, a string s and basically a verifier t here. But otherwise, I mean, having both s and t here, this b here is actually a polynomial time algorithm. And basically, we know that correspondingly has like a polynomial time circuit. The difference between S and T here, so basically, is that for a fixed instance, you know what is the corresponding S here is, but you don't know what is like a certificate. So basically, in terms of like a problem in circuit set, you just like have a part which is actually hard encoded a bit, which is actually S, and the other part which is basically some variables, and you need to figure out whether they are 0 and 1, and that is basically the part of the verifier T here. And basically, in this kind of circumstance, determining whether the original problem is actually have like a feasible solution, that whether X belongs to NP, is just equivalent to determine whether the corresponding circuit has like an output to be 1. Has a choice of the variables such that the output can be 1. Okay, so this is the proof here. So I think before I collect your questions, I guess, I mean, as I just saying that maybe this kind of proof is a little superficial, but nevertheless, let's see like a specific example along this line. So an example that we will actually probably are going to see here. So we see that we say that actually we have an example of of how this kind of circuit K is actually going to look like. So I guess in general, I mean, I'm going to talk about a little bit like a general methodology that you can construct such kind of circuit. But I guess for the convenience of making a clear presentation, so we will actually take a look at a relatively toy problem. So let's say that maybe we want to consider, I mean, maybe let's consider like a simple case of the independent set problem. So basically, as we discussed above here, let me see. I guess it's basically this part. I mean, basically, we are talking about like all these kind of reductions. So, assuming the correctness that actually the three-side problem is an NP-complete problem. Basically, here we have proven that the independent set problem is actually also an NP-complete problem. So let's take a look along this kind of line. So basically for a relatively difficult problem, that basically for the independent set problem. So let's consider like a simple case of this independent set problem. We are actually we are given a graph where we are given a graph G, and actually we want to ask actually does it contain a two-node independent set? So here we remark that the question, actually does it contain some like maybe like an L node independent set is actually just similar. But nevertheless, I guess we can give like a full detail to see the construction is to ask that whether given a graph G here, we want to ask whether actually contain a two-node independent set or not. So we basically construct like a arithmetic circuit like basically for this. So let's think about how we actually want to do that. I mean, in general, I mean, if we want to consider, like this independent set problem, this is a graph problem. So this is probably going to be a little bit. There is a distance from this graph problem, an independent set problem, to like a circuit set problem. So basically, we need to have like a transformation. I mean, basically, this transformation is going to be the part of the fact here. That basically we need to transit. I mean, like an arbitrary problem. I mean, an NP problem here to like a corresponding circuit version. So this is something we are going to specifically do here for the independent set problem. So in particular, let's consider the following way. So input that we are going to consider here is actually a graph on n nodes. And actually, if we have a graph on n nodes, so basically we have these nodes and also we have edges here. So basically we are going to represent this graph actually by n choose 2 bits. So this is as the definition of n choose 2. I mean, this just equals to n times n minus 1 over 2. This is just like to say that each bit actually just saying whether there is an edge between this pair. So I think this is something relatively imaginable that maybe, for instance, you want to encode a graph problem to like a circuit problem. Basically, you first need to transfer everything to Boolean, I mean zeros and ones, so you can basically store information of the graph. So to represent a graph, it suffices that we use n choose 2 bits. That basically, I mean, we know, for instance, assume that all the vertices, there are v1, v2 until vn here. So basically, the first bit just store the value. I mean, if it is 0, there's no edge between v1 and v2. And if it is 1, there is an edge between v1 and v2. And we just do this until basically, for instance, the pair vn minus 1 to vn and vn here. So basically, this just requires n choose 2 bits to store the information of the graph. So because we are talking about the independent set problem, so in this case, actually the certificate. So the certificate, because we are actually interested in whether actually the graph contains a two-node independent set or not. So basically here, the certificate is actually going to be n bits. So basically each bit actually saying whether a node belongs to the proposed independent set. So basically, maybe we can have like different values like zeros and ones. So basically, one is going to represent all the nodes that are currently selected, and zero are going to represent the node that is currently not selected here. So basically, for instance, maybe we can take a look at such kind of circuit. So that's actually such kind of instance and such kind of circuit. So an instance that we are actually going to consider here is that maybe we want to consider like a case where basically we have like a 3-node graph contains a 2-node independent set or not. So we actually see how we want to make such kind of construction. So let's say that maybe we have such kind of graph. So we have like a graph with vertices u, v, and w. So a graph is actually looking like this. So having such kind of graph, I mean, in general, maybe we can consider such kind of a circuit. So basically, we have a circuit. I mean, as we just mentioned, that we were actually going to represent a graph on n vertices by n choose 2 bits. So here, let's specifically for a 3-node graph, we actually are going to have these nodes. So we will actually have a node for uv and actually a node for uw and actually another node for vw. So we will actually have these nodes here. So basically, this is the part that actually we will store on the graph. And actually, on the other hand, we will have the part for the certificate. So basically, we say that this is basically the part for S. And we will actually also have a part for certificate, which is actually just going to be UVW. And basically, in this case, I mean, specifically for this graph, UVW. Basically, for this graph, we know that the value here is actually the value of the node UV here is actually equals to 1. Actually, the value for UW equals to 0, and the value for VW equals to 1. So I guess this is just like the definition that we will actually use here. So we probably need to like further figure out what is the other thing. I mean, what is basically the circuit that actually make the computation and determine whether actually this graph contains like a 2-node independent set or not. So this is something that we will actually give a check here. So basically, this is going to be on the algorithm, and actually we say that actually the efficient certificate here is actually going to check 2 things. So basically, on the one hand, we actually need to check, I mean, because we are talking about a 2-node independent set. So basically, at the very beginning, we need to actually check whether there are at least 2 values in set T. They're actually set to be 1 here. So basically, we say that the first thing we need to check is that actually at least 2 bits in T are actually set to 1. So this is the first thing that we will need to check here. So on the other hand, I mean, because we are talking about an independent set, so this is also very important because we need to make sure that this satisfies the condition of being independent. So in terms of this, and according to the definition of independent set, basically we need to make sure that actually no 2 bits in T are actually both set to 1. Actually both set to 1 if they come from an edge in the graph. They come from the 2 ends of an edge. So basically, I mean, in terms of this is actually determined by the corresponding bit in S. Okay, So these are basically the two things that we need to check if we want to make sure that we actually find we have already found a two-node independent set. So let's think about how we actually we can actually going to achieve this. So in particular, at least 2 bits in T are actually set to 1. So we just consider something like this. So actually we consider the end between U and V. So maybe let me actually draw it here. So we consider the end between U and V. And we consider the end between U and W. And also we consider the end between V and W. So what is the lesson we learned here? I mean, at least 2 bits in T are set to 1. So if this is the case, at least one of the values here is going to be 1. So the thing that we are actually going to do here is just we have the OR gate here. And basically, I mean, I probably need to pull this a little bit down here. So basically, at this point, I mean, let's say that maybe we have like a line like this. So, but nevertheless, I mean, we know that actually at this point, this is basically going to be a value returned to you that actually have at least 2 nodes being chosen. I mean, we can clearly see that if the value here, if it equals to 0, so if this equals to 0, this just means that actually, I mean, all of this, I mean, basically all of this, these values here, they're actually going to be 0. And that is going to say that actually the total number of bits that you selected is just at most 1. And actually, on the other hand, if at least 2 bits, I mean, no matter like UV, UW, or VW, the correspondingly one of them is actually going to give you a 1 value, and actually the output here is going to be a 1 here. So basically, this part of the circuit just determines whether we have actually at least chosen 2 nodes that actually with 1 here. So basically, this is the part that we address the first question that actually, in particular, this circuit actually confirms that actually at least 2 nodes in T here that are set to be 1 or not. So do you have any question about this part? Okay, so let's finish the circuit for the second part, then let's take a rest here. So for the second part, basically we need to address that actually we need to construct a circuit that whether 2 bits in T are actually both set to 1 if they come from 2 ends of the same edge. So this is something we need to further confirm. And actually, this is something that we can further confirm based on these parts. So basically, for this part, we have already made the end for each pair of vertices. So basically, this is the value for U and V, and we have the value for U and W and V and W. So for these parts, we are going to have like an interaction with correspondingly with the S vertices. These UV, UW, and VW represents whether corresponding edges in this graph or not. So we consider something like this. So basically for this U and V, we have like another end here that actually going to connect this and this. So we will actually have an end here. So basically it is going to connect UW. So basically that is going to be this. And finally, I guess, did I mess up this? Let me see. Oh, sorry. So I guess the UW, I'm actually going to connect it to this one. And here we are going to have an end that connects to the VW vertex in the S, and also the end between V and W, which is basically this. So this is basically a part, I mean, for instance, assume that if the end value here, if this value, the output is 1, this just means that this is going to be 1, and this is going to be 1. This is only going to be the case where actually U equals to 1, V equals 1, and actually there is an edge here. And this is exactly the place where we validate the condition that we are going to find an independent. So this is something that is not so good. So basically, we need to actually check all these kind of pairs, like all these kind of pairs U and V here. So basically, after we having established this, we have like all these kind of end values, and basically the remaining task is just like determining whether any of them equal to 1 or not. So basically, to confirm this, we will just like have another layer of OR here. And as I just mentioned, so basically for the second question here, we want to determine actually whether this violates the condition, the assumption that this is an independent graph or not. So basically we just need to check on whether any of them equals to 1 or not. And we just have a bunch of OR here, and then we know that actually the output of the OR here is actually just going to be like an answer to the question that have both ends of some edge in graph being chosen. So basically the output of this this part is going to be like this. So if the answer to both questions affirmative, that actually is actually going to sorry, if the answer, so basically we want the case where actually the answer of this actually to be 1 and basically the answer of this part to be 0. So this is actually going to be a good part that actually we will a good case that we will actually return. So the remaining thing is that actually we have like a NOT gate here, and actually we have an AND gate. So this is actually the final circuit that we will actually have here. So just recall what will happen if we have actually a positive output here. So if we have a 1 here, that is going to be only be the case where actually you got like a 1 here and you got a 1 here. So if you got a 1 here, you're basically going to get a 0 here. And that is going to be a case where actually we have actually chosen at least 2 of the nodes here. And actually none of none of basically for all of the edges, I mean, we consider a question basically for all of the edges in this graph, at least at most one of the vertex, I mean, of a corresponding edge, we are actually chosen here. So there cannot be the case where both ends of some edge in the graph have been chosen because the value here is just 0. And basically this is, as you can clearly see, that this is actually going to be a circuit of polynomial size, and it's actually going to answer the question whether that actually in this graph is going to have like a two-node independent subset. Okay, so let's take a break. So basically this finishes the discussion about like a corresponding circuit for this two-node independent set problem, and we have constructed this. So let's take a 10-minute break, and we will come back around 10 over 4 here. So if you have any questions, also just feel free to ask.